Let's now talk about the graphs of our two remaining trigonometric functions, the cosecant function and the secant function. And just like we have done before, we're going to relate all of these back to our unit circle. So here I have my unit circle. Notice that this angle that we start with over here is 0. We've got pi over 2 up top, pi over here on the left, 3 pi over 2 down on the bottom, and 2 pi brings us to 1 complete revolution. And thinking of our unit circle definitions, if I asked you to evaluate the cosecant of an angle theta, well, cosecant is the reciprocal of sine. We would take 1 and divide by the y coordinate. All right, so let's think about what would happen if I asked you to evaluate the cosecant of the angle 0. All right, well, here's the angle 0. We take 1 divided by the y-coordinate. 1 divided by 0 is undefined. So if I plug in 0 into the cosecant function, I have to get out undefined. If I plug in 0 in for x, I have to get out an undefined value. And just as before, whenever our trig functions are undefined, they are going to generate vertical asymptotes. So notice right here at x equals 0, I have a vertical asymptote. Okay, let's now move to pi over 2. The cosecant of pi over 2. Well, here's the angle pi over 2 on our unit circle. Cosecant is 1 divided by y. That would be 1 divided by 1, which is 1. That means when I plug in pi over 2 into my cosecant function, I have to get out 1. All right, notice my scaling here. I've got 5, 10. Let's say 1 is going to be right about here. Okay, pi over 2, comma, 1. All right, what about the cosecant of pi? Well, here's pi, 1 divided by the y-coordinate. That would be 1 over 0 again. That is undefined. So at pi on the graph of my cosecant function, I'm going to have a vertical asymptote. What about the cosecant of 3 pi over 2? Here's the angle 3 pi over 2 on the unit circle. Cosecant is 1 divided by y. That's 1 divided by negative 1, which gives us negative 1. So when I plug in 3 pi over 2, I have to get out negative 1. And what about the cosecant of 2 pi? Well, that would be 1 divided by 0, which is undefined, generating another vertical asymptote. We could do the same thing going in the opposite direction. The cosecant of negative pi over 2. Well, that would be 1 divided by negative 1, which is negative 1. The cosecant of negative pi, 1 divided by 0, undefined, vertical asymptote. The cosecant of negative 3 pi over 2, that's going to be 1 divided by 1, which is 1. So plugging in negative 3 pi over 2 has to give out 1 as an output. And the cosecant of negative 2 pi, well, that is undefined, again, creating another vertical asymptote. Okay, so we've got some important information about our graph. Now let's try to figure out what's going to happen in between each one of these vertical asymptotes. Well, notice, here we are between 0 and pi over 2. On the unit circle, angles between 0 and pi over 2 correspond to the first quadrant, and we know that the cosecant of any angle in the first quadrant must be positive. That means all my outputs in this region have to be positive, meaning that if I have a vertical asymptote here, as I approach this vertical asymptote at x equals 0 from the right-hand side, my graph must go up. Again, my outputs must all be positive. Okay? Now, from pi over 2 to pi, well, that corresponds to angles on the unit circle that are between pi over 2 and pi. That would be the second quadrant. Cosecant is 1 over y. We know that the y-coordinates in the second quadrant have to be positive, which means that the outputs have to be positive, meaning that my graph, all the y values must remain positive, and as we approach this next vertical asymptote from the left, our graph is going to go up. Okay, between pi and 3 pi over 2. That brings us down here into the third quadrant. And cosecant in the third quadrant is negative. That means all of my outputs here have to be negative. They must be below the x-axis. Well, that means that as I approach this vertical asymptote from the right-hand side, my graph must go down to negative infinity. And from pi over 2 to 2 pi, that corresponds to, 3 pi over 2 to 2 pi. 3 pi over 2 to 2 pi. That corresponds to our fourth quadrant. And we know that cosecant is also going to be negative in the fourth quadrant, meaning that as we approach this next vertical asymptote from the left-hand side, my graph must go down to negative infinity. Okay, well, now that we know what this single period of our cosecant function looks like, we can get a good idea of what's going to happen over here on the left-hand side of the graph. Yes, the function is going to repeat itself. All right, and there we have the sketch of our parent function. All right, let me erase my messy penmanship out of the way here so we have a better idea of what the graph looks like. All right, there we have the graph of y equals the cosecant of x. All right, so what is the period of the graph? Well, period is how long it takes for the function to repeat itself. And notice that that has to include one u, which has a minimum value here, a relative minimum, and one upside down u, which has a maximum value. So one period has to contain each one of those. This function repeats itself every 2 pi. All right, what about the range of this function? Well, the range is a little bit interesting here. The range is from negative infinity to negative 1 with a bracket. It hits negative 1 here, right? We reach that value. And then from 1 to positive infinity. Notice again the bracket on 1. Okay, it reaches 1 and then it goes up from there. There is the range of our function. And our domain. Notice that, again, we're going to have an infinite number of vertical asymptotes. There are an infinite number of values for which the function is undefined. So we're going to say our domain is all real numbers except x cannot equal. We pick a vertical asymptote. Let's pick the one that's at x equals 0. So x cannot equal 0 plus n times however frequently they occur. Well, notice that we actually have a vertical asymptote every pi. That's every half period. So we say the domain, all real numbers except x cannot equal 0 plus n pi. Well, that just simplifies into n times pi. That is the graph of y equals cosecant of x. One cool thing to recognize here is that if I graph y equals the sine of x, which we see here in green, all right, every single maximum of our sine function corresponds to a relative minimum of our cosecant function, and every single minimum of our sine function corresponds to a relative maximum of our cosecant function. Also, the zeros, or x-intercepts of our sine function, correspond to each one of our vertical asymptotes. All right, there we have the graph of cosecant of x. Let's do the same thing here with y equals the secant of x. So relating it to our unit circle. Here's my unit circle, 0 here on the right, pi over 2 up top, pi on the left, 3 pi over 2 on the bottom, and 1 complete revolution brings us to 2 pi. And to evaluate the secant of an angle theta on the unit circle, well, that's the reciprocal of our trig function. On the unit circle, we would take 1 divided by the x-coordinate of our particular angle. All right, and so just like we have done before, let's start with the angle 0. If I asked you to evaluate the secant of 0, we have 1 divided by the x-coordinate associated with the angle 0. That would be 1. And 1 over 1 gives us 1. That means if I plug in 0 into my secant function, I have to get out 1. Here's x equals 0. And right about here, that's x equals 1. Now let's evaluate the secant of pi over 2. That would be 1 divided by 0. Well, 1 divided by 0 is undefined, and anywhere our trig functions are undefined, we are going to have a vertical asymptote. Let's now go to pi. The secant of pi, 1 divided by the x-coordinate here is negative 1. 1 divided by negative 1, that's negative 1. So when I plug pi into my secant trig function, I have to get out negative 1. There we go. All right. The secant of 3 pi over 2, that would be 1 divided by 0, undefined. The secant of 2 pi, 1 divided by 1, that gives me 1. And we could do the exact same thing going in the opposite direction. The secant of negative pi over 2. Negative pi over 2 being down here. 1 divided by x is 1 divided by 0, undefined. The secant of negative pi. 1 divided by negative 1. That's negative 1. Secant of negative 3 pi over 2. Brings me up here. 1 divided by 0, undefined. And the secant of negative 2 pi, well, 1 divided by 1 gives me an output of 1. Okay, and we can use the same process. Here I have angles between 0 and pi over 2, right? Here's 0, here's x equals pi over 2. On the unit circle, that's the first quadrant. And we know that secant in the first quadrant has to be positive. Therefore, all my outputs of my secant function between 0 and pi over 2 have to be positive, meaning that as I approach this vertical asymptote, my graph must go up. Okay? And if we look at values of x between 0 and negative pi over 2, on the unit circle, 0 and negative pi over 2 corresponds to the fourth quadrant. And secant, 1 over x, is also going to be positive in the fourth quadrant. Therefore, all my y values here, all my outputs have to be positive, meaning that as I approach this vertical asymptote, it must go up to positive infinity. All right, and between pi over 2 and pi, that corresponds to the third quadrant on the unit circle. Secant is negative. My graph must go down to negative infinity as we approach this vertical asymptote from the right-hand side. And pi to 3 pi over 2. I come to the unit circle. Pi to 3 pi over 2. That's quadrant number 3. And secant, 1 over x, will be negative again, meaning my graph must go down as we approach this next vertical asymptote here at 3 pi over 2. Okay, and so now that we've seen a few of these graphs, these trig functions, we know that they're going to repeat themselves. Boom, there I have the graph of y equals the secant of x. All right, so let me clear this off a little bit, clean it up. The graph of y equals the secant of x. Let's now talk about the period of this function. How long does it take for this function to repeat itself? Now, remember, in order for it to repeat itself, it has to include one u and one upside down u. Well, if I go from negative pi over 2 to 3 pi over 2, that means my period is 2 pi. I could also look at that from one relative minimum to the next relative minimum. That takes 2 pi. The period of my secant function is 2 pi. The range of y equals secant of x, well, that's going to be negative infinity to negative 1, right? From negative infinity up to negative 1 with a bracket on negative 1 because we include that value. It hits y equals negative 1. And from positive 1 to infinity. Here's y equals positive 1, and the graph goes up to positive infinity. Our domain. Again, we have to account for all of the possible vertical asymptotes. So we say the domain is all real numbers except x cannot equal. We pick a vertical asymptote. Here I have one at pi over 2, and add on n times however frequently they occur. Notice that they occur every pi units. That's every half period. So we say x cannot equal pi over 2 plus n pi. Again, pick one of the vertical asymptotes. This one's pi over 2. Add n times however frequently they occur. There is a vertical asymptote every pi, so we have n times pi. And if you were to graph the reciprocal of secant, that would be y equals cosine of x, notice that every single maximum of our cosine function corresponds to a relative minimum of our secant function. Every minimum of cosine corresponds to a relative maximum of our secant. Every zero of our cosine function corresponds to a vertical asymptote of our secant function. All right, so there we have it. The graphs of our parent functions, y equals cosecant of x and y equals the secant of x. You guessed it, in the next video, we're going to talk about transforming these functions.